All right, today we're going to take one of the most fundamental facts in all of physics and show you why it might not be a fact at all. Because it turns out what we think we know about the speed of light is actually based on a huge assumption that we can never, ever prove.
So I want to start with a statement that sounds, frankly, completely absurd. No one has ever measured the one-way speed of light. Now, I know what you're thinking. That's got to be wrong, right? I mean, we see the number everywhere.
Because we all know this number. It's c, the speed of light. Exactly 299,792,458 meters per second. It's not an estimate, there are no decimal places, no rounding. It's one of the most precise and important constants in the entire universe.
In fact, we are so incredibly certain of this number that, since 1983, we've literally used it to define what a meter is. Our most basic unit of length is defined by the speed of light. So, if our definition of a meter itself relies on this number, how on earth is it possible that the one-way speed has never actually been measured?
Well, the answer is hiding in this really cool paradox that gets to the very heart of how we think about reality. See, it turns out that measuring the speed of light isn't nearly as simple as measuring, the speed of a baseball.
Clocking a fastball is easy, right? You just need to know the distance between 2 points, and you time how long it takes the ball to get from A to B. Simple. But with light, you hit a fundamental wall. If you shoot a laser from point A, how can you possibly know the exact instant it arrives at point B when your only clock is back at the start? With you.
Okay, so the obvious solution, right? Just use 2 clocks. Put one at the start and one at the finish. But this creates an even bigger and, as it turns out, a completely unsolvable problem. So for this 2-clock experiment to work, they have to be perfectly, and I mean perfectly, synchronized. But how do you actually do that? How can you guarantee with absolute certainty that 2 clocks, separated by some distance, are showing the exact same time, down to the nanosecond?
You immediately run into a catch-22. You could try sending an electrical pulse down a wire to start them both at the same time, but that signal travels at nearly the speed of light, which is the very thing you're trying to measure in the first place. So, okay, what if you sync them right next to each other and then just carry one to the destination? Well, thanks to Einstein's special relativity, we know that a moving clock actually ticks slower than a stationary one. By the time it gets there, it's already out of sync.
So if a one-way measurement is impossible, then what in the world have physicists been measuring all this time? The answer is a clever workaround. They measure the light on a round trip. This idea was first used successfully way back in 1849. A guy named Hippolyte Fizeau shone a light at a mirror 8 kilometers away and timed how long it took for that light to come back. And this is the key. Every single major experiment since then has used this exact same principle. A single clock at a single location, timing a round trip.
And that brings us right to the core of this entire explainer. All we have ever known, all we can ever know, is the average speed of light on a round trip. We've never, not once, actually clocked it on a one-way journey.
Now this might seem like just a little technicality, but stick with me, because this is where things get truly weird. It opens up a mind-bending possibility. What if the speed of light isn't actually the same in all directions? What if our universe is fundamentally asymmetrical?
Okay, think about this. Let's say we're communicating with an astronaut on Mars. We send a message and we get a reply 20 minutes later. We naturally assume our signal took 10 minutes to get there and their reply took 10 minutes to get back. Makes sense. But what if our message actually took the entire 20 minutes to get there, traveling at half the speed of light, and the reply came back instantaneously? From our perspective here on Earth, the total time is still 20 minutes. There would be absolutely no way for us to tell the difference.
The consequences of that are just bizarre to think about. In that asymmetrical universe, an astronaut looking at Earth would be seeing our 20-minute-old past. But we, looking back at Mars, would be seeing them in real time. We could look at a star hundreds of light years away and see it not as it was centuries ago, but as it is right now. And the craziest part? All the laws of physics that we know and love would still work perfectly in either scenario.
So, how did physics solve this massive, unsolvable puzzle? Well, spoiler alert, it didn't. Instead, Albert Einstein just made a really clever and, honestly, a very practical choice. In his famous 1905 paper on special relativity, Einstein himself pointed this out. He wrote that we have to establish, and this is his word, by definition, that the speed of light is the same in both directions.
He even put by definition in italics, almost like he was winking at us, saying, hey, just so we're all clear, this is an agreement we're making, not a fact we've actually measured.
And that choice is now known as the Einstein synchronization convention. It's the simple, elegant assumption that light travels at the same speed in all directions because, hey, it's the simplest explanation and it makes all the math work out beautifully. But at its core, it is fundamentally a choice.
He later called it a stipulation that he could make of his own free will. I mean, think about that phrasing. That is a shockingly subjective way to describe what we all think of as a rock-solid objective law of nature. He basically just chose a definition for, at the same time, that made the universe simpler to describe.
So, if all the physics works out either way, why does any of this even matter? Who cares? Well, because buried deep inside this puzzle is a direct challenge to one of our most fundamental concepts, the very idea of now.
You know, most physicists just point to Occam's razor. The simplest explanation is probably the best one. And they just accept the convention so they can get on with their work. And that's fair. But the puzzle itself, it reveals a hard limit to our knowledge. It's a wall we can't see past. And for some people, it might even be a clue pointing toward a deeper, more unified theory of everything.
Which leaves us all with one final, profound question to chew on. If we can never, ever truly know if two distant clocks are actually synchronized, does a universal now even exist? Does it make any sense at all to ask what time it is right now on Mars?